In undergraduate graph theory, we have learned about Turan theorem. So, Turan theorem says that if you have a graph G, n vertex graph G, which has more than, say, 1 minus 1 over r plus 1, r minus 1, let's say, times n choose 2, then G contains a complete graph on r vertices. Let's say more here. So, in Turan theory, extremal graph theory or Turan theory, what we are interested in is this extremal function, which is the, say, maximum number of edges in G, which has n vertex G's, doesn't have a H as a subgraph. So this actually determines the extremal number of KR. And also Kobari-Shoshi-Turan theorem we have learned, showing that the extremal number of n KST, the complete bipartite graph, is big O of n to the 2 minus 1 over s, where s is smaller than t. So we learned about this, extremal number. And I will not repeat the things there, but we learned that for graph which is not bipartite, the Eredich-Stone-Simonovich theorem more or less tells us the asymptotic value of this extremal number. So which is more or less we know the extremal number, this Turan number, extremal number, that's what we call this. But for bipartite graph, we don't know much. For this Kobari-Shoshi-Turan gives us an upper bound on the, this extremal number of complete bipartite graph. But the lower bound is only known when t is sufficiently smaller than s. So even this, we don't know, even this simple case of complete bipartite graph, we don't know the full answer. And now we will learn a technique to prove the following theorem. So we want to generalize this Kobari-Shoshi-Turan theorem a bit by showing the following using the alteration method. Let's say S is a natural number and H is a bipartite graph with vertex partition AB such that all vertices in B has degree and most s. Then there is a constant C which only depends on H, such that the extremal number of this H is C times n to the 2 minus 1 over s. So this generalizes the Kobari-Shoshi-Turan because if you have S vertices and T vertices, and if this is complete, then let this be A and this be B, and every vertex here has a degree at most S. So this satisfies this condition. But this is not only the one graph that satisfies this. It could be that there are two S vertices and there are T vertices, and each vertex is adjacent to half of that in some arbitrary fashion. Then this says that this also satisfies this upper bound on the extremal number. So we want to prove this. And what does this say? So in order to say that, say this, we want to show that if we have an n vertex graph G with a number of edges bigger than this, then this implies that we can find H inside of G. So this is what we want to prove. So that provides this upper bound on the extremal number. Because if we have more edges, then we can actually find the subgraph H inside of G. So now our goal is that assume we have a graph with many edges. And then somehow there we want to find the subgraph H. And H has this condition that one part has vertices which has bounded degree. So what do we do? One of the natural way is that when we have H, which consists of the vertices in A and vertices in B, let's say you order these vertices x1 to x2 to say x, I don't know, H. And here we have y1 to some number. And one of the ways that if we have G, and yeah, for now we can simply assume that G is also bipartite, because we can take a max cut of G, which will lose the half of the edges. So we delete the edges here, but half of the edges, but I mean, we just want to show this with certain C. So we just increase our initial C by twice. Then, I mean, after deleting half of the edges, the G still satisfies, I mean, this condition with the smaller C. So here, now what we do is so recall that this is independent set. There is no edge between. So if we map this vertex into vertices here, then no bad thing happen. So when I say bad thing is that if there is two vertices adjacent here, this is mapped here and this is mapped to here, but there is no edge, then that's bad event. So we want to find the H inside of G. How do we do it? We want to map each vertex to here and each vertex to here, so that if there is an edge, then we get an edge. Then at the end, we find the subgraph of G, which is isomorphic to H. So we call this embedding. So we want to embed these vertices here so that the adjacencies are preserved. For that purpose, once we just embed the vertices in A, then no bad event happen. But while doing that, we want to ensure that say S vertices, all S vertices here has large common neighbor. So somehow we want to ensure that. So these mapped vertices, this image in these vertices in G, let's say we know that these three vertices has a large common neighbor, and then this Y happen to have these three vertices here as its neighbor. Then if this has this common neighbor, I mean, large neighborhood, let's write. So it has, I mean, there are many vertices which is a neighbor of these three. Then if we embed this Y into here, then these three edges, adjacencies, are all preserved, automatically preserved here. And for other vertices now, say Y prime, again it has some S vertices which has which is already embedded here. And if this has also large common neighborhood, then you can just embed these two on here. So this shows that embedding this H into G, so finding H inside of G, can be boiled down into the problem of putting these vertices into here in this independent set, so that every S vertices here has large common neighborhood. If we can ensure that, let's say this is U, then we want to kind of show that to ensure that every S vertices, let's just write R for now to be consistent with consistent with the lemma that we will write later. So S or R, some number of the U have at least say some number common neighbors. So this is what we want to ensure. And then later this M, we want to take it as big as B. Then, you can always, you don't have to worry that these common neighborhoods are already occupied by the other vertices. So as long as this happens. So that's what we want to do. And then this can be actually ensured by using alteration method, proving this lemma. So let some numbers are given, and G is an n vertex graph with average degree D. And if there exists T such that D to the T over n to the T minus 1 minus n choose R times m over n to the T is at least A. So whatever this expression means, it's not too much important as long as you understand the proof. If you understand the proof, then this expression will be natural. Then there exists a subset U of Bg with size at least A such that every R vertices in U have at least M common neighbors in G. So for now, you don't have to really understand what this expression means, but if some condition holds, then we can find the set of vertices where it is not too small. Then every R vertices there have large common neighborhood. So many common neighbors. So what we want to do is we want to use alteration method. Somehow we want to choose some set so that let's say we have this W1 and W2, two sets. Before that, let's write this. So we add a star. So many cases, if we write this neighborhood of G or neighborhood of this vertex set, it could mean two things. Either union of all neighborhood of the vertices in there, or intersection of the neighborhood of the vertices there. The latter is called the common neighborhood, and then first one is usually called neighborhood. So this could mean either one of these two, depending on which book you read or depending on which paper you read. But as we already have used this in undergraduate graph theory, so I will introduce a new notation. Let's put star here, which is not really standard notation, but for us, let's just write this as a common neighborhood. So for example, if we have a one vertex whose neighbor is here, and then one vertex whose neighbor is here, UB, then N G star of UB is this X and W, then this is X and W. So let's say you have a two set W and W2 such that I will omit the subscript if it is clear. These two are different in this way. This W1 has a larger common neighborhood. And we want to somehow choose a set S at random. And then we want to make sure that the W1 is more likely to be inside S than W2. So this is what we want to ensure. Then somehow what we use this S, and then we want to, ensure that the most of the sets in here, let's say with the size R, most of the sets of size R here have a large common neighborhood, and then only small number of sets are bad, then we will kill them somehow by deleting some vertices. So that's roughly our plan. But how can we ensure, how can we randomly choose this set so that the W1 is more likely to be included in W2? One of the ways is that you choose a random vertex V and let this S be the neighborhood of this. So you took a vertex at random and then you consider its neighborhood. Then what's the probability that this W is inside the S? Then that's the probability that you have this W1 and you choose one vertex and its neighborhood contains W1 is same as this V actually lies inside of the common neighborhood of W1. So this happens if V is a neighbor of every vertex in W. So this is probability that V is inside the common neighborhood of W1. And since V is randomly chosen, this is that. And by our assumption, this is strictly bigger than the common neighborhood size of W2 over N, which is again probability that W2 is inside of S. So this kind of suggests that maybe we want to choose a vertex at random and then consider its neighborhood. And more generally, slightly more generally, now what we will do is the following. For this, it was a motivation of the following proof. For each I in T, we choose a random vertex, Vi. So here we choose only one vertex V, but we want to choose several vertex independently, uniformly at random. So this means that Vi equal to Bj could happen. So it's not necessarily disjoint vertices. So you choose one vertex and you choose second vertex, third vertex, and same vertex could be chosen. And let say A be the common neighborhood of these T vertices. And let's say X be the size of A, be the random variable denoting the size of A. Then what's the expectation of this X? Which is, we have to take all the vertices and then we compute the probability that that vertex lies inside of A. Because each of this is random one, so you have V and you have the neighborhood and then outside. If V1 is here and V2 is here and V3 is here and all VTs are inside of this neighborhood, then V is in A. Which happens, each of the which happens with the probability that say degree of V over N to the T, which is N to the negative T, summation of all degree to the T. Now let's consider the function, this function. then T is at least 1, so this is convex. So convex functions are x, y, and this is half plus x plus y. Then fx plus fy over 2 is bigger than f of x plus y over 2. And this can be generalized into n values. So what we can conclude, let's write it this way. So 1 minus t, 1 over n. This is by using convexity, n to the 1 minus t, and 1 over n, summation of degree v to t. And this is, what do we get? This is the at least d, so that's average degree. So this is d to the t over n to the t minus 1. Now we have this 1. And then now we see how good this set A is, whether it contains some W of size R with a small common neighborhood. For that, let's say script R is a set of all, sets of size R whose common neighborhood has size smaller than or equal to M. And let Y be the random variable counting the number of subsets R which of A, which is size R such that let's just write it this way. R is inside of this script R. So this bad set. Then what's the expected size of Y? Expected number R is the summation of all R inside of this R. You compute the probability that this lies inside of A, which is what? Again, common neighborhood size of R over n to the t by the same logic as here. So again, you have R and it has small common neighbor, and B1 here, B2 here, and all BT, B1 to BT must lie inside of here so that this is in A, which happens with this probability. But how many R's here? At most n choose R. And then what's this? From the definition, the above one is at most M. So we get this expression. Then what do we get? By linearity of expectation, we know that the expected size of x minus y is d to the t over n to the t minus 1 minus n choose r times m over n to the t, which is exactly the expression here. And this says that this is at least A, meaning that this is at least A. So this implies that there exists choice B1 to BT, which yields x minus y is at least A. And we consider it's a set A with this. Consider such a set A, and we delete one vertex from each subset R which lies in this script R, lying entirely inside A, and let U be the set of remaining vertices. And U has size x minus y, which is at least A. And what do you know? Every R subset of U has a common neighborhood size at least M. And U is our desired subset. So this proves this lemma. So here, how did we choose U? We choose some other thing we want to be T. And then that gives us some set U. So this U actually depends on other choice. So we choose this U in a dependent way. So we call this method or this lemma as dependent random choice. So by using this, we can prove our goal, the theorem about this two-round number of the bipartite graph, where the one part has a bounded maximum degree. How do we prove? We let A be the size of A, B be the size of B, M be, say, A plus B, and D be 2 times C times n to the 1 minus 1 over S, where C is some number bigger than 3 times AMA. So these numbers are chosen so that later we can actually embed one vertices by one vertices into, vertices in H into vertices in G, one by one, and then make sure that no bad thing happens. Suppose that G is an n vertex graph with number of edges at least C times n to the 2 minus 1 over S. Then average degree is LSD. And with above choice, what we know is we have d to the s over n to the s minus 1 minus n to the s times m over n to the s is, you can actually compute it. You can do the computation. Then this is actually bigger than or equal to A. Thus, the dependent random choice implies, the dependent random choice lemma that we proved, the previous one, implies that there exists a set U with size A, at least A, such that any S vertices in U has at least M common neighbors. So now we are ready to actually find a copy of H in G. In other words, we want to embed one of the vertices in H into G one by one, so that the adjacencies are preserved. Take an arbitrary map V from A to U, and let B be the vertices, say y1 to yb. And we want to embed them one by one. So in order from y1 to yb, one by one, right before we embed, say, xyi, we have what? The common neighborhood in G of neighborhood of xi, yi in H. this is at least M, which is A plus B. So what we have H, A, B, and G. Here we have U. So again, we have this yi, which has this neighborhood. And then this pi maps them to here. So we have these three vertices here. And then we know that the common neighborhood of these three are big, have size M, at least M. So some of them might be already occupied by pi yj with j smaller than I. But this size is at least A plus B. And some of them are okay. Actually, this could be looking this way because they could have a common neighbor inside of U, right? So some of them could be already occupied by pi of x, not x, x, or some x inside of A. But all of them together, except yi, all of them together is at most A plus B minus 1. But this has size at least A plus B. Thus, there exists a vertex vi inside of this common neighborhood that we are interested in. Which is not an image of any vertices in A union x1 to xi minus 1. So we map, this is y1 to y minus 1. We map yi into vi. And we just repeat this. We show that H is a subgraph of G. So this proves this theorem, which shows that an upper bound on the extremal number of the bipart type graph, whose one part has bounded maximum degree. So yeah, this is the end of today's lecture. Yeah, we will see. Let's meet again in next lecture.